Welcome to Demystifying Math. In this lesson we're going to be using the limit definition to find derivatives. Recall that the derivative is really just a formula that helps us find the slope of a function. We can use the limit definition, which is as delta x goes to 0, the function evaluated x plus delta x minus the function itself divided by delta x is the derivative of the function. That's going to give us a formula, and then we would evaluate the formula at a specific value of x in order to find the slope of the tangent line at that particular point. In this lesson, we're going to be focusing on finding the derivatives, or the formulas, for the slope and using the limit definition. So let's start off with an example. Suppose we had f of x is equal to 3, which is really just y equals 3. Well, if we're looking at y equals 3, you should know that that is a horizontal line and that the slope of any horizontal line is 0. So we expect that our derivative will be 0. Now remember that when you're looking at that limit definition, the numerator, when we have f of x plus delta x minus f of x, is really just our y2 minus our y1. Well, our y values when we're looking at a horizontal line are exactly the same. So our numerator in this case is just going to be 3 minus 3 because our y values are always 3. Now our x values can change and be just about anything, but we want the difference between our x values to be extremely small or close to 0. So in our numerator we have 3 minus 3, which is 0, and 0 divided by delta x, which is a really small number, is still going to be 0. So our slope is going to be 0. And that can be true for any value that we have a constant for our function. So anytime that we have a horizontal line, we're going to get our derivatives equal to 0. So I just use f of x equals b, where b represents any constant. Okay, let's try another example. Suppose we had the function 1/2 x minus 3. Well, you already know this to be a straight line, or a linear function. And this one is an oblique line. It's not horizontal or vertical. And we know that the slope of this line is 1/2. So we expect our derivative to be 1/2. It should not vary at all in this particular case because it's a linear function. So let's go ahead and evaluate our limit. So we're going to take x and replace it with x plus delta x for the first term in our numerator, and then minus the f of x function itself, so minusing 1/2 x minus 3, and dividing by delta x. So let's go ahead and distribute the 1/2. And then what we should see is that the 1/2 x and the negative 3 canceled out with the f of x function. So we're just left with 1/2 times delta x divided by delta x. And in this case, the delta x's are canceling out. So we just have our limit as delta x goes to 0, 1/2. Since there is no delta x left, we're just left with 1/2, which is what we expected our slope to be 1/2 for the linear function. So we could probably do this. We could say, well, for any function that is linear, and we'll put it as ax plus b, the derivative is going to be the slope, which is a. You should notice that the constant term canceled out. In this case, we had those 3's there. And that's going to happen every time. And we should expect that because on the previous slide we just showed that the derivative of any constant is 0. So it doesn't matter that whether or not we're adding or subtracting a constant to any function, that derivative is going to go to 0. Okay, let's find the derivative of x squared. So plugging into our limit definition, we have x plus delta x all squared minus x squared in our numerator, and dividing by delta x. Okay, so x plus delta x is binomial, and we're going to square it, so that means that we have to FOIL that out. And then we're going to subtract x squared from that. So our x squared terms cancel out, and we're left with 2x times delta x plus delta x all squared, divided by delta x. So we're going to factor out and cancel the delta x's. So we're left with 2x plus delta x, and then we're going to take the limit of that as delta x goes to 0. So the delta x term is 0, and we're left with 2x. So that's our formula for the derivative of x squared. Okay, so what if we have a multiple of x squared, a k in front? Let's see what would happen then. So we have k times the function f of x. And the limit of that is equal to the limit of k times the limit of f of x. So we can pull that k out in front. So since we know what the limit of f of x is, in this case our x squared function was 2x, then we're just going to multiply it by k. So that gives us a constant multiple rule. For any function, let's say h of x equal to k times the function f of x, your derivative is going to be k times the derivative of the function f. Pretty easy to do. So a constant multiple really doesn't affect your answer too much. Let's try to find the derivative of kx squared plus ax. In this case, we're adding and subtracting two different functions, and we have a limit rule on that. So if you have the limit of two functions that are added or subtracted, you can take the limit of them separately. So m prime of x would just be 2kx plus a, taking the limit of each one of those functions separately. And that gives us a sum and difference rule for derivatives. So h prime of x is going to be f prime of x plus or minus g prime of x, taking the limits separately, taking the derivative separately. Okay, let's find the derivative of f of x equal x to the third. So we're going to plug into our limit definition, and this time we have a binomial that's cubed, so we have to expand that out. And you can do that using any rules that you want, or you can work it out on your own, but it's expanded out here. And then you should notice that the x to the thirds are going to cancel out, and then everything has a delta x in it, so we're going to divide those out. And then we want to take the limit as delta x goes to 0. So our first and last terms canceled out, and we were left with 3x squared. Okay, going back to what we just saw. When we had something like g of x equal x to the first power, what's happening is that we ended up with 1, or whatever its multiple is. If we had 2 times x, it would end up being 2, and so on. If we have x squared, we got 2x as our final answer, and x to the third gave us 3x squared. Well, what you should notice is that each time that we took the derivative, we were 1 degree less on our exponent. And also notice that the exponent became a multiple of x. So that gives us a power rule, where we have any function that's x to a power, the derivative is going to be that power times x to 1 degree less, to the n minus 1. And that's a pretty easy rule for us to find and use without having to go through the limit definition. So let's say that we wanted to find the derivative of 5x to the fourth plus 2x to the third plus x squared minus 7x minus 10. Well, we're going to be using our constant multiple rule, our sum and difference rule, and our power rules here. So looking at the 5x to the fourth individually and taking that derivative first, you would do 5 times 4x to the third. For the 2x to the third, you would have 2 times the derivative of x to the third, which is 3x squared. For x squared, we're going to reduce our exponent by 1 and bring the 2 in front of the x as a product, 2x to the 1. With the minus 7x, the derivative of x is 1, so we're just left with negative 7. And the negative 10 is a constant, so that derivative is going to be 0. So our final answer is 20x to the third plus 6x squared plus 2x minus 7. Okay, so the power rule works for polynomials as we just seen, but it also works for any exponent that we can have. So looking at this particular example, we have 5x to the 2/3. We're going to follow our power rule to find the derivative. So again, we have a constant multiple of 5. Taking the derivative of x to the 2/3, we would bring the 2/3 in front as a product of x and reduce our exponent by 1. So 2/3 minus 1, or 2/3 minus 3/3, gives us negative 1/3. And then I just multiplied our 5 times the 2/3. So we have 10/3 times x to the negative 1/3. Or if you want to write it without a negative exponent, 10 over 3x to the 1/3. Let's try one more. So suppose that we were given the 5th root of x to the 7th. The first thing that you want to do is rewrite that as a power. So that's going to be x to the 7/5. And then what you want to do is take the derivative of that. So the 7/5 comes in front as a product of x, and reduce your exponent by 1. So you have 7/5 x to the 2/5. So remembering some of these power rules will help you a lot, so you don't have to go through your limit definition to find the derivatives. Thank you for tuning in to Demystifying Math.